I will be recording this. So thank you all for joining us today. Our webinar is going to be talking about groundwater modeling at mine sites, dewatering, reactive transport, and more using FEFLOW. So your instructor for today is Dr. Carlos Rivera Villareyes, and he actually works as the Director of Sales Support and Service at DHI WASI in Germany. Carlos has trained professionals all around the world in all different types of groundwater modeling topics, and he has this profound knowledge of groundwater and unsaturated zone modeling, as well as parameter estimation. So we have quite a few people that registered for this webinar, and I think they're just going to continue to trickle in. So because of that, we ask that if you think of a question during his presentation, go ahead and enter it in the chat screen, but that will wait and answer those at the end. So with that, let's go ahead and get started.
Yeah, thank you, Jennifer, for the introduction, and thank you everyone for your interest and also coming to this webinar today. So the topic of this presentation is quite interesting. It's a complex topic because we have to take care of multiple aspects on groundwater modeling. So not just flow, also reactive transport, chemical species. Maybe this topic is also associated to geotechnical applications, so geomechanical applications, etc. So I will try to give you a quick overview of the multiple options and tools that we have here in DHI with our software FEFLOW for accounting all these different scenarios. No? I will finish my presentation at the very end with a small live demonstration about lithium brine modeling. So let's start with the presentation. A FEFLOW modeling tool. A FEFLOW is a tool which includes all the system characteristics, so you can have in one single tool all the relevant processes. This means flow, mass transport, heat transport, a combination of these three, couple of these three processes, so the so-called thermohaline simulations, even interaction with surface water, etc. FEFLOW is very powerful for physical processes, but at the same time, we also spend quite some investment for visualization tools. So you can really visualize quite well the different results and complex geometry in 2D, 3D, make cross sections, as you can see here. It's really straightforward. We also have strategies to identify worst case scenarios. So we have a tool called FEPES, parameter estimation software. No, it's a graphical interface for PES, which allows us to identify all these cases and be prepared and take smart decisions. No? So how can actually FEFLOW help you in this context of mining applications? So we can account all the system complexity with our unstructured meshes. We do really have very handsy unstructured meshes since the versions FEFLOW 7.0 and now with the versions 7.1 we have enhanced and make these workflows even more robust. So I will show you a couple of ideas what you can do with unstructured meshes. So you can take the most complex geological model, put it into the FEFLOW, generate a mesh. You can use our in-house tools or layer configurator to, by your own, without the need of external geological software, you can also create a complex geometry. We have stable and efficiency numerical schemes and methods. So we have also called automatic time stepping approach, which basically design smartly where has to be calculated, no? And this allows us to accelerate the simulation processes and also at the same time maintain a very good balances and accurate solution. We have a professional and a flexible user interface. Solute and heat transport is supported. We have specific tools for simulating open and closed loop geothermal systems. We also have multiple access for interfacing with softwares like Mike21 for coupling of surface water, Mike11 or Mike Hydro River for the interaction between 1D surface bodies and groundwater. We have a premium user support. There are free viewer options, visualizations, also for post-processing. And last but not least, we are doing this stuff since the 70s, so we have really quite a strong background here. Now we are very familiar with the markets in mining, so we have multiple projects worldwide, and from all these projects we have learned and tried to improve the software in such a manner that is a handy solution for all these mining applications. So modeling at mine sites, there are multiple applications that you actually take care, no? So if we just focus on the mine, so we have the pits, no? Maybe you have some underground facilities, no? You're interested to estimate the dewatering, so what are the volumes that you need to pump out from the system, no? Because you care about the slope stability. So all these informations can be done straightforward with the software. You want to simulate tailing facilities to see if there is possible infiltration from the tailing water to the natural groundwater system. No, you want to simulate cases of reactive transport. So no problem. We have a tool which can couple FreakC, the reactive transport engine, with FEFLOW to do a really complex redox cases. You want to simulate the mine closure, the peak lake. Also, we have multiple in-house solutions now to simulate the formation of lakes, the interaction between atmospheric fluxes and groundwater. Acid mine water drainage, so you can also simulate with our multiple tools for reactive transport. All these processes are embedded in a regional scale, so we can account this without a problem. We also have tools for surface-water interaction. Either if it's a river or it's a lake, you can simulate this just in FEFLOW, or you want to do a hydrodynamic robust solution. We have in DHI options for simulating this with Mike21 flexible mesh. Which can couple with FEFLOW in a really straightforward manner, Or you want to simulate the case of flooding events, here in the mine. You can also use these tools for such a purpose. So there are multiple things that are required in this modeling. So I just kind of pick up the most related or most relevant tasks for mine water management. So you're interested to have efficient dewatering, So you can, with the software, you can estimate the volumes that you want to extract. Okay, this can do any software, but we also have capabilities to optimize this process. Now some years ago, we have a project where we actually, in an automatic manner, identify the location of the wells, which can minimize the cost and also maximize the efficiency of the dewater. This can be done with multiple scripting capabilities of the software, so you either can write your own scripts and produce these multiple scenarios, You can use our interface with FEPS to actually solve the inverse problem and identify where are the position of the wells to have the minimum cost and the maximum efficiency, Other typical tasks here, forecast of mine flooding effects, a scenario-based risk evaluation. So what is the worst case scenario? Maybe there is an infiltration from the tailing system to the groundwater system, so you want to avoid these cases, so you can run also a FEPS optimization in predictive mode to estimate what is the worst case scenario here. Multiple tasks in mining is seepage estimation. So here as I mentioned, we are interested in the worst case analysis, position of our wells, and how we should pump out water from the system. Regional impact. So what is the effect of the groundwater table drawdown? So there is possible release of the distribution of contaminants, slope stability, location of water levels, pressure distribution of pit walls, and optimization of drainage. So we have tools for this. Now, if you want to simulate a drainage, we have methods which can simplify a solution in 1D with the so-called discrete picture elements. I'm going to explain this in the next slides. Rebound and reclamation forecasts. What are the challenges of all these different tasks? Is we are in the multi-scale problem, and multi-scales because we have local processes happening around the mines, underground system, drainage, etc. No, but typically we build these models in a regional scales because we are interested to investigate what is happening at that scale. No, and also we don't want to have effects of boundary conditions here. All the processes are always transient, so it's happening in excavation over time. So you can simulate in FEFLOW these geometrical changes during the simulation with just one single model. This is something very nice because in the past you have to, if you want to have multiple excavation scenarios, no, or multiple scenarios with different mining plans, so one used to have multiple maybe FEFLOW models. Now you can just do it with one single model and adjust the model geometry by a so-called element deactivation. You can also simulate the case of deposition over time. This is an example where you want to accumulate tailings in the system. You want to change the geometry of these tailings, no? So you can also use the same technique here. Transient dewatering and rebound. So we have simple methods to assign transient boundary conditions, either seepages, tailings, etc. No? Complex geometries is always the case here. So we are always dealing with some of complex geology without really clear layer structure. Now, I will focus this special part more in detail later, no? But our new methods for unstructured meshes actually give us a lot of flexibility to deal these cases, no? So we can handle quite well pinch out of layers, faults, fractures, no? Also, if you want, you have some inclined elements in 1D, I don't know, maybe you want to simulate some horizontal drainage, etc., or you have horizontal wells or inclined wells. You can do it straightforward with FEFLOW 7.1. Integration of technical processes, drainage, dewatering. Other type of challenges are physical processes happening, density affected flow. Maybe you are simulated or you're working in a case of a brine injection system, no, or disposal of salt or potash mines, or you are in a nowadays so popular lithium exploration. Also, all these processes are density dependent. Also, you need to have a stable software for this, which can simulate flow equations, mass transport equations, even multi-species transport in cases needed, no, and couple these equations by the density terms in multiple aspects. Process coupling, I mentioned several times, a typical example is the river flow, but you can also couple with multiple software. Now, once I saw a presentation of a customer doing not a coupling, but interfacing, I would call it, between FEFLOW and a geological software. Now, so I mean, FEFLOW can simulate the flow, you get the pressure distributions, you can export maybe by some scripts this pressure distribution, pass it to your technical software now, and then estimate slope stability. Calibrations is a big topic here, scenarios, uncertainty analysis, so we have to have multiple and smart options now for the calibration and certain analysis. So we use here as a our PES integration with FEFLOW now. We have multiple options of parallelizations locally in a server or even in the cloud that is becoming popular nowadays. So you can all use these technologies in any kind of architecture. Okay, multiple needs that we have in these cases are. So here I have a representation of a mine pit during operation, or it could be also after rebound. No? So you have let's say, a complex geometry. So you need to handle this. You have volume changes from one position to another. You need to also have a software which can deactivate or activate these volumes. And as I mentioned, we need also a smart way to handle boundary conditions. So let me give you a few options that you can use with our software. So complex geometry is a typical case. Here I try to point out three main cases. Now we have fracture of faults. What you can see in the upper left corner. We have excavations which define certain geometry. You want to include this geometry maybe in your finite element mesh or in the groundwater model. And you have some local layer pinch outs, which can be very simple like this one here, or can be also very complex. So what I can offer you is our solution with partially and fully unstructured meshes. Here are a couple of examples what you can do. From the most simple example is here, this one in the lower right corner, where we have a 2D mesh, which can be triangular or quadrilateral mesh. And this, you have the flexibility to combine multiple types of elements. In 3D, you can have a fully unstructured model. You can see here an example of a pit. You can have layer pinch outs, etc. And here there is a case of a fracture or of a fault here, which has been fully discretized. So why you actually need this flexibility in meshes? The reason is very simple, because first you want to include most complex geometries. Second, you want to have a model which runs fast enough to do multiple scenarios and actually play around with the model. Because what do you do if you can create a large model, complex, but at the end you end up with many elements and takes multiple days to run the problem? So we have meshes, or we have tools where you can optimize your mesh design. So you can use smart techniques to have local refinements in 2D and 3D, and really spend the necessary amount of nodes and elements in these locations where you are very interested. In the other locations, the regional scale, maybe you can play around with more large element sizes, because you are not too you don't need too much details in this far location. So we have these tools in 2D since the beginning of the software. Since the very beginning of the software, we can also build triangular and structured meshes. Combination with quadrilaterals. Now, since 2 years ago, we extend the problem to 3D, and we can cover many aspects of unstructured meshes. So we have multiple workflows, and they are very convenient because they cover almost all the possibilities that of the user. So you can build your own model by just using FEFLOW, or you can use our interoperability with other softwares like GoCAD, GeoModeler, Leapfrog, etc., to import this geological data and build complex models. So let me show you a couple of workflows here. So you can take the simple workflow, where is basically build your 2D super mesh. Super mesh for us means our conceptual model. Our conceptual model, where we actually indicate what are the areas of interest. Okay, we have some points because here we want to put our dewatering wells. We have polygons because these are areas of interest. Maybe we have the tailings, so we have some polygons of the pit shell projection, etc. So you can build your 2D super mesh, construct a 2D mesh and a structure with triangles or quadrilaterals, extrude the model to 3D, and you can stop here and just work with a 3D layer mesh system. But if it's necessary, you can decide, okay, I have my 3D model layer base, I can do it partially unstructured. Maybe there are some intersecting layers, some pinch out, etc. So you can use our tools to locally add tetrahedral elements to the system. Or if you want to convert your 3D layer model in a totally unstructured model, so you can also do that from this point. The other workflow is more direct. We have the concept of a 3D super mesh, which is basically the same conceptual model but now in 3D. We have some faults, maybe some contact surfaces between geologies, and etc. You can build this geometry by multiple file formats, from the more simple formats like DAT files or text files, shed files in 3D, or more sophisticated solutions using a geological software. And build this 3D and super mesh, and here FEFLOW, if the geometry is clear enough, can construct a 3D and structural mesh at the beginning. And there are multiple advantages here because how you prepare the data can help you to accelerate the processes. So you can, if you already know that you have multiple geological units, you can set your input data in a smart manner that FEFLOW can store these elements inside the unit in multiple groups, which then makes really easy to assign material properties. You just need one single click, activate the group, and then set your conductivity 10 to the minus 4 meters per second, for example. So main strategies for 3D is where it's possible, you can use mesh with layer prisms. Where it's necessary, you can embed in structural tetrahedral meshes. Maybe you want to do some incorporation of artificial underground extractions in mining, pipes, etc. You can do also local tetrahedrization for the case of layer intersection or pinchings or faults. And when you have a clean and structural information, so geological model, so you can generate a fully unstructured or full tetrahedral mesh. So there are three main workflows, which I would like to show you here. So the first one is the most simple workflow. You have a model in FEFLOW and you want to put a new structure. So you can now simply make a selection, the region where you want to modify, pass this region with drag and drop to a meshing panel and generate a new geometry inside. We are here basically remeshing, not refining. So we end up with new configuration of elements in this specific volume. And this gives us the chance to pass any file formats, point, line, or polygons to this volume during the remeshing process. So we can actually create a mesh acknowledging this input geometry. So you have a file, you can just simply drag and drop polyline shed file, and then FEFLOW and TechGen will make sure that this path will be in the new generated mesh. Second workflow requires structural data, so either a geological software or you build your conceptual model by multiple polygon files like shed files or any other format. I know people using AutoCatalog to build these polygons and surfaces. So this is an example of interfaces of geological units. So here you can see a bit structural data. These are the layer rings here. This is the clipped tetrahedrons in the structure mesh. So if you imagine to build such a problem with a classical layer, it can be done, of course, but you will definitely have much more elements here, And this is the fully unstructured mesh of this example. The workflow number 3 is actually one of my favorites because as a user give you completely control on the process. So we have enhanced our layer configurator significantly, where you can manipulate the elevation data quite easily, just simply drag and drop, and also use this layer configurator to build your conceptual model. There are simple rules where, for example, if you're doing interpolation and a certain surface is intersecting another, there are some rules which can tell the layer configurator how to decide which is the surface that has predominance here. So where the interpolation should stop or should begin. And there are so many options, so you can even combine this with some macro recording. So if you have a very complex model, then you can just press a button, record your process. Then the next time you want to test a different 2D mesh, you can just play start, go for a coffee, and wait that the model is built automatically. Here you can see, for example, we have a topography here now. Then we have a layer in yellow intersecting the topography. So here at cropping now. So and you have the bottom of the layer intersecting here. So how you can build this in FEFLOW very easily? In FEFLOW we have layers and slices. Slices are two surfaces which define a layer, it's a volume. So you can say your topography, slice 1, you can say your bottom of the model, slice N. Fix this, and then you add additional slices to build this layer in yellow. Because you have fixed or classified the layers as non-movable before, then these new slices are actually intersecting here, and FEFLOW will connect them automatically. Then you are done with this layer, you can go with the layer in red color and repeat the same process. Then there is this conflict of a slice or layer intersection. Then the software offers you multiple options how you can handle this. If you want to do it in the classical way, there is an option where you can preserve the layer continuity. So this means that FEFLOW will maintain a minimum thickness in these intersecting areas. You can do a local refinement. So in these areas where, on this location where there is intersection, we can use other type of elements. So tetrahedrals here. Or you can just remesh the entire layer with tetrahedrals. Or if you want, you can refine the entire model in 3D in location with and without intersection with tetrahedrals. Because we are in a continuous development in the software, we have enhanced all this flexible meshing in the current version, and we are keep doing the same stuff with the next release. So we have parallelized quite a lot of these operations of remeshing. They are relatively fast. We also have additional controls for add-ins. So if you have, for example, a fault, you want to create certain buffers around, so you can just simply use some percentage factors to control the size of the elements. If you have a model which is already parameterized, and you want to add new structures, so you end up, I told you, you end up with a new mesh, new number of elements. So we have methods to do interpolation, a 3D parameterization. So you can decide how to migrate properties from your old mesh to the new mesh. Of course, as I mentioned, we enrich a lot the layer configurator. And more about meshing and mining is the possibility to actually deactivate the model. So deactivation of the model means that basically you mimic the process of deleting a part of the finite element mesh temporarily, and you can control this with time series. So in this simple example, we have 1, 2, and 3 levels of this open pit, and you can decide, like, after a few years of simulation, deactivate layer 1 or level 1, then 5 years more level 2, and so on layer 3. You can control automatically this with time series. If you want to do for the case of tailing accumulation, it's the opposite. You start with a high geometry. At the beginning is everything deactivated, and then you start activated during the simulation. Multiple tools for model conceptualization. Just I pick up some of the tools. If you have any specific wish or question, you can always ask me at the end of the presentation, or type your question here in the chat. One feature, one option that we always emphasize is the use of the so-called discrete feature elements. We emphasize this option because it simplifies a lot the complexity of the problem. So here basically we have the possibility to reduce the dimension of the process. So if you have a fracture, you have a fall, this can be simulated with a 2D surface and not with a 3D small volumes here. If you have a pipe, you have a tunnel, you can simulate this system as a 1D element. In the past, or until the version 7.0, you could always add additional conductivity or dispersivity to the system, to this element, to this discrete feature element, because they are part of the mesh, they are connected to the matrix. So we solve the equations of the nodes, and they get contribution from the matrix and from the discrete feature elements. Since the version 7.1, we implement a so-called dual node method, which basically simulates imaginary nodes which are connected along your fold and your matrix. And this set of imaginary nodes can try to mimic certain separation between your fault and your matrix, so this with a so-called coupling length. Depending on this coupling length, you can slightly retardate the exchange of fluid, mass, or heat between the fault and matrix, or vice versa. No? And this is a very nice approach, because you can even now put observation points in your faults, in your matrix, now in the same coordinates, but you can see these different values or different differentiation on the pressure, because they could be separated from each other. The same approach is used when we spoke later about the coupling between surface water. We also have a 2D discrete feature element, which is used for the exchange of fluxes between surface water software and groundwater here. This is the next part. So what we are using here is our tool MI21 flexible mesh. We can simulate complex scenarios of hydrodynamics, no, in 2D, and with the possibility of having a flexible mesh. It fits quite well the concept of FEFLOW. The coupling is really done quite easily. So you prepare your input data in FEFLOW. Input data is just one single thing, is to prepare a discrete feature. So basically you select the area which will be set to the coupling. Then there is a so-called mic simulation engine, simulation launcher, which can directly take your FEFLOW model and run also MI21 flexible mesh. Here for MI21, we have the possibility to use GPU computing, which accelerates strongly the simulation. Typical applications and rainfall, surface runoff, infiltration, ponded water phenomena. Here, for example, if you want to simulate a flooded mine, or you have the pit lake, maybe you want to also have a hydrodynamic process here, so you can do it with this coupling option. Surface flooding events, storm events, dam breaks is also a hot topic here in mining. So you can also include these extractions in the surface water and see the effect of these dam breaks in groundwater. Groundwater flooding events, so the other way around. You want to see what is happening above the ground. River aquifer interactions, coastal settings, also river aquifer interactions, industrial porous media, etc. FEPS is our tool for automatic calibration, is our package that we have been developing since version 6.2. 6.2 was the first version of FEPS, that was the beta version, and then we released the official version in 7.0, and now in 7.1 version we include quite a lot of new features now. FEPS is the graphical interface, the very famous software PES, developed by John Doherty in Australia, and brings you a lot of flexibility, so you can parallelize, calibrate your FEFLOW model really fast. Fast in terms, we save you a lot of time in the preparation of the multiple input files for PES. You get the benefits of a nice and simple graphical interface, so you see what you want to see, your objective function, your scatter plot, your time series, and some statistics related to the calibration. But you also get access to the multiple output of PES in case you are an experienced user and you want to look more in detail all this information. No? We can parameterize the model with constant pilot points in 2D, pilot points in 3D, for structured layers, for unstructured layers. So all the possibilities that you can imagine, they are included here. We have methods for regularization, mathematical regularization, the so-called SVD assist, to reduce the number of dimensions of the problem and accelerate a little bit the calibration process. We have tools for regularization on the conceptual model, the so-called Tikhonov regularization, where you can create rules to guide tests during the calibration and have a strong and also good calibrated parameters which fulfill your conceptual model of conductivity, rupture, etc. And export of the result is pretty easy. You are done with the calibration, just one click, and then you get all the calibrated parameters in a new FEFLOW file. out-of-the-box solutions. I name it out-of-the-box because they are not really common, but are really nice that you get to know them because it can help you for multiple things, and not just in mining. So one is our plugin FEFLOW PyFreeze, which we developed a couple of years ago by the interest of a company in Canada to simulate so-called freezing wall. So we extend the phase in the ice phase here in the FEFLOW flow solution by introducing this plugin. Basically, this allows you to have a freezing function which can control certain properties like conductivity for the flow, porosity, and also other heat properties. No, so you can we basically extend the definition of our porosity by including an ice phase here and there of so-called liquid phase saturation. So what is the part of the fluid volume which can be subjected to freezing, no? And with the user-defined freezing function, we can decide how is the degree of freezing for multiple materials. You can control the conductivity, you know Richard's equations to reduce conductivity due to saturation. Now you can have a conductivity reduction due to freezing, no? Etc. So here I have a nice video which simulates the injection of a refrigerant into the system. You can see that the soil is being freezing, the wall is closing. You can see the flow velocity vector, which are basically departing and moving around your freezing wall. This is a very straightforward solution. We have the advanced reactive transport, which is a coupling between the very famous FreeXC software developed by the USGS and FEFLOW. Basically, you can do the entire set of reactive transport in FreeXC and couple all this with FEFLOW. No? I mean, the reason of having this coupling is because FreeXC can handle quite well reactive transport, and we can do quite nice multiple things in fluid transport, including variable saturated conditions, 3D Richards equation. We can solve mass transport, heat transport, and edge transport, and we can combine all this with FreeXC. We do this approach by our open programming interface, which allows the interaction of the solver or also of the simulation. You can pass or get multiple things during the flow, mass, and heat transport solutions. And we use this approach to solve and couple this geochemical simulation with FreeXC and FEFLOW. Interface is very simple. You need the same things that you will use in FreeXC: initial conditions, boundary condition, a database for the reactions. Multiple applications are all the redox reactions that you can imagine, dissolution of minerals, surface complexation, gas phase exchange, temperature pressure dependent reactions, no? Advanced calculation of density, etc. One very popular feature nowadays is our scripting capabilities. It's really popular because you can almost do everything that you can imagine here. You can control the software, you can manipulate parameters, set boundary conditions, adjust conductivity, quite simple with Python. And Python is a nice language, programming language. Is very easy to learn and also to catch up. There are multiple tutorials, online courses, etc. I mean, I also don't have I don't have an IT programming background, but I learned this by my own, and I can tell you that it's very simple to understand and read. So FEFLOW Python interface implementing our old IFM programming interface based on C++. Whatever you could do in C++, you can do also in Python, or almost, no? You have options to load the documents, save the documents, run the simulation from a Python interface, create a DAC. If you imagine, you can put this in a loop, you can do a scenario analysis, very simple. Here, you can, so all the simulation controls. You can also interact with a simulation by passing information in the different callbacks, no? So pre-time steps, you want to change your conductivity because you want to have a simulation of a dissolution, of a certain mineral, so you can adjust this conductivity due to concentration at the so-called pre-time step before the solution is being calculated. You can control licenses. All language features applicable to Python are available here. No? You can run it from outside FEFLOW, but we also have a nice graphical interface for small scripting inside FEFLOW. I'm going to show you my example here. No requirement for a compiler or installation of a third-party software. And I call FEFLOW Python is a IFM plus because it's advanced. And I put it here. You can actually have almost not limits here. Before I move to the live demonstration, I would like to give some announcements. No? Our main announcement today is our FEFLOW training opportunities. So as today we have also a webinar later the year in October 11th, so my dewatering and pore pressure modeling in a complex geologic system. And we have multiple training courses worldwide, so if you're in Australia, Germany, Mexico, USA, or India, so please look our website for the different events in your area. And this year we also have the FEFLOW International User Conference 2018, Groundwater Modeling in a Digital World. We have very interesting presentations, no? Nice keynote speakers. We have offers of training, workshops, and everything is in a really convenient, awesome price of less than $400 US. If you're interested in advanced training and improve your FEFLOW skills, here in Germany we also do our so-called FEFLOW e-learning program. We have been doing this since I think it's already 3 years, and it's appreciated by many users because it's quite convenient because of the times. Also, you save on accommodation, on travel costs. It's an online program where you can learn mass transport and reactive transport, Python interfacing. This is an advanced part that we are offering for the first time here, where we show interaction with multiple packages. So, for example, you always prepare your report with images. Now you used to do some maybe Excel graphs. So I will show you how you can automatize this and create thousands of images in just a couple of lines in scripting. And you can reuse these scripts for all your projects that you have. Modeling your thermal applications, groundwater modeling of open cast mining. We focus here a lot on unstructured meshes, so how you build the pit geometry here and put a temporal transient boundary conditions. And we have a new course, really interesting one, and it's Introduction to Density-Driven from Mining Applications. We have received multiple requests for many guys interested in doing lithium exploration, brine injection, so they really want to do some FEFLOW stuff here. So we developed this nice course, just 6 hours, to give you nice ideas and easy how you can set up, for example, an evaporation boundary condition, how you can control the evaporation due to the depth to groundwater. I will want to show you some stuff today in this demonstration, how you set a boundary condition for the mass transport, what is the importances or what are the different approaches for boundary conditions for mass transport, how you control a nice mass balance, how you estimate your lithium based from the mass concentration, etc. So all these applications will be covered in this course, and the price is also very convenient. And if you really have any question, you will have my email at the end of the presentation. You can just simply send me an email, or you can just visit our website here, the Academy by DHI.com. There is a section related to e-learning. Then there is also a section related to the standard courses. So this one here. Okay, live demonstration. We have a prepared example of lithium brines. It's really an introductory example, just to give you a first idea what I'm going to show you in our training course in November. So let me share my screen and and show you our setup. I have multiple versions of this file. let's see. Yeah, that one. Okay, so the model domain is pretty simple because of times I will not show you how I construct the model. Just let me explain you a few things of this problem. So let me put the conductivity here. So this is the conductivity. We simulate an area where there is high evaporation in the system. So let's imagine you have your so-called salar here in this area, and you have a recharge coming from the mountain. So there is a alluvial system here. There is also recharge from the left and high evaporation here on the middle of the model domain. The other side, so the north and the south, there are no flow boundary conditions here. Typically, if you want to set evaporation in FEFLOW for this system, you have two alternatives. So actually three alternatives. So you have the so-called in-out from top-bottom. Many of you might know this boundary. It's basically a fixed of described flux, meters per day or millimeters per year. You can have a fluid flux PC, which basically has the same units, or I know some guys doing a so-called fluid transfer BC. So you can just simulate a certain head, which can be the head of the funding water on the salar, no? And with this head and a linear relationship control the outflow from the groundwater to the atmosphere. These options I'm going to discuss also in our training course. Today I'm going to show you this in-out from top-bottom. So let me change the units here to something more readable in millimeters per year. So we have 350 millimeters per year. Okay, I have set up and run the model in multiple scenarios. So first scenario, would like to show you what is the importance of having a dependency of a transient evaporative boundary condition here. In our first scenario, we just have a constant evaporation, and I want to see what is happening with the model. So there is no steady state solution here. Basically, I try to identify a quasi-steady state solution. And why I do it like this? Because this is also a problem of mass transport. Maybe we also want to simulate density-dependent processes here. So it's unrealistic and also unpractical to achieve a steady state solution for a very nonlinear system, which is Fisher's equation here, because we solve unsaturated flow, and on the top of that, we put more nonlinearity with the density term. So basically, you cannot identify appropriate steady state solutions. So here, I simulate a transient solution with constant boundary conditions, constant evaporation, and leave the model running for certain time and see what is the evolution, how is the evolution of the system. So we solve Richard's equation, transient, and I just pick a very long number for the simulation. We simulate here 10 years run. So actually, you even don't need to define initial conditions. So what I'm doing here is basically saturated my entire system. So I have a saturated system, and I want to see what is happening after 10 years, or 100 years, 1,000 years of simulation. There should be certain equilibrium, right? So just let me go to this is the DAG file, so I can just maybe go to the hydraulic head. It's more interesting here. So we can also put this up. This is my slice view, but maybe it's more interesting to show you the cross-section view. So I have cut the model from west to east, no? And this is what I'm going to show you. These are the nice FEFLOW visualization options that we have. So here I display my pressure, I put my position at the phreatic level. So you will be wondering, okay, why I have multiple phreatic levels? We start with a fully saturated system, no? As I told you, there will be certain equilibrium after some years of simulation. So we can just move front through the system. Take some time because of the sharing the screen. So you can also see in the 3D view there is a decrease of hydraulic head strongly in the area where I'm forcing evaporation. I will just go farther in the simulation here. So the water level is also stabilizing. Here we have a local water level system and there is a strong decrease of hydraulic heads here. The elevation of the model are about 4,200 meters and here is about 1,500 something, no? So here you have a negative hydraulic heads. We are doing unsaturated program. We solve Richard's equation and we have a empirical definition for the unsaturated parameters. We use modified Van Noten parameters here. And I will go farther in simulation, just maybe here. And then you will see what is happening. So now my effect of the evaporation is really strong. So I have even a very negative pressure here. And if I continue doing this, I will see that there is a drawdown even touching my bottom of the aquifer. So if I look my fluid rate, which is basically my when I have recorded multiple bags, I have a constant outflow coming through this evaporative boundary at the solar. So now let's make the problem more fancy, and I want to have a boundary condition which change according to the water depth. And to do that, you have multiple options. I know some guys doing some expressions here, but I wanted to do it in a more, let's say, flexible manner. So what I did here, yeah. So what I did is I can show you. I use our scripting capabilities in FEFLOW. So there is this nice option in 7.1 called scripting, which you can activate from the global settings, and you can add your own script. So you can put your, I have a function here, so I just quickly show you, which can compute the depth to groundwater. And this function can be written in C++ or in Python. If you have in C++, you will have to compile a plugin and put it here. I have it in Python. So this function has the advantage that I can edit it every time that I want, easily. The function will be automatically called during the model runs and create a distribution called compute depth to groundwater. And this distribution is automatically stored here. And let me go and repeat the process here. So we start from not from pressure 0, but we start from a condition where there is no evaporation, just the heads. Let's take some. So if I look my hydraulic head here, and this is my initial conditions. Then in this position, let's go to the cross section again. You can see, by the way, the mesh. So my entire profile is almost saturated. You see here the water level. I start with this condition, and now I start evaporating the boundary condition. Evaporating the system. And the trick here is very simple. Once this computed depth to groundwater is estimated, then FEFLOW allows you to use some expressions here. So you can relate your in-out from top bottom, which before was 350 millimeters per year constant, to this one. And you can use a linear function, exponential function, as you like. This is one way, or you can even write this function into your script easily. So now you can see here, it's happening something in the model. So I have a decrease of the hydraulic head. I will just go farther here on the year. Let's go to the last one. There is not much time. Yep. Okay, this is my last condition here after multiple years of run. I want to check the fluid rate bucket, and this is my evaporation. At the beginning, we have a constant, more or less a constant evaporation because we have high pressure in the system. The water level is almost touching the topography. Then there is a decrease of the phreatic surface, and there is also a decrease of my outflow, until there is certain equilibrium. If you remember, if we go back to the case, I'm going to sport this line here. This is my case of, I already sported actually. This is my case with constant evaporation. I'm going to put it here in this one. There should be certain relationship, right? If not, I'm doing something that is not correct, so I just go for presentation. And of course, it's not defined here. I'm going to export it again. Sorry for that. So right click, properties, save. Operation. Okay, and now we go to the previous model, import this, constant evaporation. You see, it's actually coinciding. So I have constant evaporation in the first days or years of simulation, and then the system gets to equilibrium, and I have a reduction of evaporation because the water level does not change significantly. Then I can take these conditions and do a mass transfer because I need to initialize the concentration of lithium or total dissolved solids. You can repeat some kind of the same picture. No, that is not the one to show you now. So a case where a steady state solution, a case where there is no concentration, just in a deeper part of the system. So if I show you a cross section here, concentration. We start with these conditions, so where we say, okay, here is my deep location of the halide. So I would like to initialize and see what is happening with the concentration. There is a high concentration here because it's a salt, and run the problem for multiple years. Everything is constant. I have this evaporation depending on the water depth, and then I can get my initialization of concentration very simple. And this is my concentration here. And when you have the initial conditions of concentration, you can do exploration model where you can basically start pumping out certain. So I put some wells in this last model. Let me show you the wells. So multi-layer wells here you see. There are just 4 of them here, and you can monitor nicely what is the concentration of in multiple locations in the system due to pumping conditions. So we can go local concentration, and there is a decrease of concentration in certain locations. So if here are my observation wells, really close to the vicinity of the wells. Okay, this was really a fast demonstration. In case you have any questions, so you can just, we have the time now to answer all these questions. I will start with those written on the chat. Are the scripts for optimizing wells positions available to users? Not really, Reinhard, because they have developed for model specific or project specific situations. We can always, DHI can always offer you a solution for that, if you're interested for a specific project. Okay, Stefan, does the new formulated discrete feature elements allow one to simulate pipelines carrying mine water from wells to some other locations in the model? I guess you mean here with a closed pipe, no? Yeah, I mean, you have this option of arbitrary path, node path, where basically allows only exchange of fluid, mass, and heat at the beginning and the end of the pipeline. Whatever happens in between, there is no outflow. I hope this answered your question, Javier. One of the challenges in the first versions of unstructured mesh in FEFLOW was that element selection for parameterization of water balances had to be defined in advance and could not be updated once the mesh was constructed. I am correct? And if so, has changed? Yeah, I'm trying to understand what you mean. Basically, with our layer configurator now, we store all this information, so you can, when you construct a model and you decide to make certain pinching out between layers, the layer configurator will automatically create the selections of the different layers. So the real selections, so where exists a layer, these selections then they are available in the selections panel. You can just use it for assigning material properties or any other. You also get to store the content of geological surface as a phase selection, so you can place a fall if you want or any other property. And all the rest of selections has to be done via scripting. So we create kind of a lot of scripts for creating selections. So I can, if you're interested, you can send me an email and I can give you some tips how you can do that by scripting. Hey Nilsson, is there an interface between MyShe and FEFLOW? If no, how to best to couple Richard estimates and FEFLOW? Well, there is not really it's an official solution. I think Alexander Renz was writing some time ago some interfacing by reading the outputs from MyShe and put it then as a in-out from top bottom parameter in FEFLOW. They should be all plugins. I'm not sure if it's keep it up to date, but also if you're interested, I can try to look more information. Okay, any other question?
Hello, I have a question here.
Yes, sure, go ahead.
But you know, when we this is related to the second question about discrete feature element. So let's say the one that you have here, your model here. For example, I want to introduce the pipe underneath, subsurface pipe. So is that now you can show the result of the reduced pressure? Because in the past we are not able to show the effect of that pipe because of reducing the pressure.
Yeah, let me show you something, Monsieur. It's not really with pressure, but it's with concentration, but basically it's really the same principle. This is our online help, by the way, parameter types, discrete features, dual node connector. So you can create such a separation between your pipe, discrete feature, fracture with these dual nodes. And depending on your so-called coupling length, so the distance, this imaginary distance between your common nodes of definite elements and the dual nodes. So here is the representation. You can have multiple cases. No? So here, I have, let's say, conductivity in the connector, so the 1D connector which separate your pipe fracture between to the matrix has also conductivity and a length. So here I have a very small conductivity of this separation or this connector, no? You see here there is maybe it's difficult to see, but in the breakthrough there are 2 points. They share exactly the same coordinates, but one is put it on the matrix and the other is put it in the so-called dual nodes. And they have different levels of concentration. And the concentration basically goes like on a pipe, just straightforward. And then I start modifying, increasing the conductivity of my connector, and you see now there is a more interaction between these two systems. Increase more, and you also see the breakthrough curve. And look in this point, there is this certain separation, and now these two are fully coupled. This is the case where you are talking about they have the same pressure, temperature, or concentration. But with this method you can enhance and provide certain decoupled process. I hope this answered the question, Munse.
Yeah. So dual node is a new here in this case.
Dual node is a new, it's a version, it's only available in 7.1.
Okay, thank you.
Yeah, sure. Okay, we have another question here in the chat. Which geological modeling software do you recommend to use for structural mesh generation? Okay. A political question. Yes, I'll tell you, we have interoperability with GoCAD, GeoModeler 3D, and Leapfrog. All of them, they can provide input to FEFLOW. all of them can also fail because the typical workflow in geological modeling is that they can do a very nice and interpolation, fill, create a different volume, etc. But some of these can fail in cases where they have to triangulate. Because they have to triangulate the context of your geological systems or units, no? And this triangulation are read by FEFLOW and we use as a constraint for the 3D mesh. So you need to always play around with this triangulation. No? Some of the software offer you more options than the others. So, for example, GeoModeler 3D, developed in Australia, they have nice options for triangulation. They use a very powerful also mesh generator called Sigal, developed by the geological server in France. And they can also create tetrahedral meshes that we can't import in FEFLOW, and you don't have to anymore construct a mesh in FEFLOW, so you just need to parameterize. So this one is kind of stable, no. But I also have experience with GoCAD, no. It also really depends on the complexity of the system, no. So for a simple geometry, maybe all of the software can do a good job. For a very specific case, there is one maybe better than the other. Yeah, and thanks a lot for the webinar. Yeah, okay, that answered you already, Jennifer. Okay, I hope I answered all of them. Okay, any other question?
One more here, is that okay?
Yeah, go ahead.
Yeah, you mentioned one of your slides. You mentioned about the parallelization in FEFLOW in cloud.
Yeah.
Are you talking about the this SaaS portal is now FEFLOW is active there?
Yeah, we have this. Yeah, you're right. This SaaS, no, software as a service for FEFLOW, so you can rent it there. But I was mainly talking in general because so you can take our solution, no. But you can also just go to any other provider like Amazon, for example, or Azure. No, they also offer high computational options. No, you need to install FEFLOW, and FIPS can work in this, and you can have a parallelization. So we have done also multiple projects with call-out parallelization for mining cases, and it's quite convenient because the prices are not that bad. No, I think that time was kind of $3-4 per hour, one of the most powerful solutions. So yeah, so you need to have, in all the cases, you need to have a FEFLOW corporate license because you need to share the license between the multiple instances. This is one aspect. So either our software as a service solution by DHI, any cloud provider, but we are also working in a so-called Docker containers for FEFLOW 7.2. Docker is, you can see it as a virtual machine, but with the difference that is really more portable. So you can just basically easily activate your simulations and your software. You can just download whatever you want and distribute it and put it in most of the situations. No, and my colleague is basically developing an option to deploy these parallelizations in FIPS, in the FIPS concept via this Docker containers context. Okay.
So, it's not clear yet, though. In that SaaS portal, is that people are already active there? Before it's not, right?
Yeah, before was not. It's active. You can just
already active. Okay.
Yeah, you can rent. There are multiple templates. It's for sure in the one of all the mics, no, and you can just rent it and use it, no.
Okay.
Okay, I think we are running out of time and even over the time, 10 per minute, so I probably have to finish here. Yes, so thank you for participating in this webinar. As Jennifer said, she's going to send the presentation and additional information to all of you. From my side, yeah, thank you for your time. I hope I draw your interest in multiple topics. If you have any questions, so here is my email address, so you can just go ahead and directly send me an email. So have a good time and thank you. Bye-bye.
Thanks, Carlos.
Thanks, everyone. Thanks, Carlos.
Thank you.
Thanks, Jennifer, too.
Thank Jen.